Yeah, thanks very much for the invitation. Indeed, I was prepared that this is a public talk, so I made it very non-algorithmic. I hope that it is not going to get to be boring for you, because you are expecting algorithms. So I'll talk about applications mostly. And I was also expecting that some of you might not know where I'm sitting right now. So Leiden University, first university in the Netherlands, founded by William of Orange in 1575. And it was actually a reward for Leiden's resistance against the Spanish invaders. They could actually decide between a tax reduction and a university. Wise choice, I think. And we are in the Department of Science, where we can collaborate with physics and astronomy and so on. So it's pretty cool. And what you see here is the academy building where the PhD defenses take place. As you can see, it's an old church. Frank has seen it, I think. So it's a pretty cool place. Yes, and of course, that's where we are. So he mentioned Dortmund. As you can see, that's also not too far away. It's actually a driving distance, 2 hours, 15 minutes, order of magnitude. And that's where PPSN is taking place. So if you are interested, of course, you have PPSN on your radar screen. We discussed this already. Now, this is my overview of the talk. Brief intro. I will talk about evolutionary optimization and product development. I will talk about solution analysis. I will talk about multi-criteria optimization and solution mining. A little bit about automated machine learning for simulation data, which essentially is response surface methods, production process examples with machine learning, and some conclusions. And I'll probably get stuck somewhere, so I will observe the time and make sure that I'm done within 45 minutes from now. The background of all of this is, in my opinion, a very nice analogy. So I give you a second to read this, where we can reflect about what it's all about in terms of evolution. And there's, of course, one of the arguments here that biology is somehow engineering solutions. And of course, that's exactly what we are using in evolutionary computation to allow for finding good solutions to complex optimization problems. And of course, most of you will be familiar with this loop, which I've been using for almost 30 years now to explain kind of the iteration loop of evolutionary computation, where we have a population of candidate solutions. We have selection operators, recombination operators, and mutation operators. But of course, there are also mathematical descriptions of all of this, which we could pop up quickly here, which are, in the classical perspective, differentiating between binary representations in a GA and continuous representations in an evolution strategy. All of us know that, meanwhile, there are all kinds of mixed and complex representations and mixtures between these algorithms, but this is a simplified view, as you know. Now, population doesn't sound very efficient because you have lots of solution candidates and lots of iterations. Most of you will know that there are wonderful counterexamples, which I will explain in a moment, where these algorithms are used in a very efficient manner. Since I'm going to talk a little bit about, obviously AI in general too, I'm trying to avoid a definition of AI. As we all know, this is more complex than we think. But I found this very nice picture that actually positions evolutionary computation at the intersection between machine learning and natural computation, with some overlap to neural computation, which of course contains deep learning, which most people think about when they hear about artificial intelligence. But also the role of evolutionary computation in machine learning and AI should not be underestimated, because as we all know, most, or actually all algorithms in AI also contain an optimizer. This is a very nice paper that Wolfgang and some of his collaborators actually published in the ACM computing survey. Going a step further, what is machine learning? Found this nice classification on the internet that actually differentiates between supervised learning, unsupervised learning, and reinforcement learning. And very simplified, my position is that in principle, you could say supervised learning is data with a dependent variable that depends on input parameters. We call that the output parameter. and unsupervised learning doesn't have that dependent variable. I know this is very simplifying, but it helps to differentiate, especially later on when I talk about product design optimization and process optimization, where we will have a dependent variable that is quality, for example, and describes the quality of a product that is being manufactured, and you would like to understand how this is affected by the processing and the material parameters. Okay, these are the preliminaries. I mentioned that I wanted to talk about efficient evolutionary optimization in product development. And of course, I need to show you the example that I always show, which is Hans Paul's experiment, which he did in the 70s. And without going too much into the details, this is an experimental optimization using evolutionary computation, actually an evolutionary strategy, a so-called 1+1 strategy, where he was building one nozzle at a time, measured the quality of those nozzles, then generated a new one by mutation, created the new one, measured the quality of the new one. If it was an improvement, he kept it. If it got worse, he went back to the previous one. And then after 255 experiments, the nozzle design that you see in the bottom right corner was evolved. And interestingly, unimaginable by human experts, it was actually 32% more efficient than the initial nozzle, which was a very simple design that had been proposed by the experts to start with. I said before, this is an experiment from the 70s, which was published in this publication. And I think it's still an extremely interesting example showing that evolutionary strategies, evolutionary computation, can be extremely efficient. Many of you have been using maybe 1, lambda type algorithms, even in a genetic algorithm setting where only mutation is being used. You have very small population sizes, and you can be very efficient in finding a good solution with a small number of experiments. Nowadays, most of our experiments actually look different. Nowadays, we are moving from running a real-world experiments very often to using a simulator. For example, for this kind of applications, final experimentation is still being done, but of course, all of the car development takes place based on simulations. And to give you an example, what it typically would look like, nowadays you have very complex simulations. So the picture on the left-hand side is taken from a recent paper which we published at Cooke this year, which shows a side impact crash simulation. So the idea is that there's a standardized pole experiment. You see the pole here, the car hits the pole from the side. And in particular with modern cars where you see the battery down here at the bottom of the car, you need to take, of course, precautions that when you hit such a pole that the battery does not get impacted to an extent that actually creates a really difficult situation like a fire, for example. In such simulation-based loops, it typically looks like the bottom right side where you have a simulator, it gets some input, typically the car design, it generates some output, and there's an expert who tunes the parameters. Of course, we all see immediately that it shouldn't be like this, but it should be like this. You have the output, you compute some quality measures of the output, and you have an optimizer that is actually tuning the parameters. Everybody of us would be immediately happy if we see this image because we understand the idea. In many industries, they would say, though, we really don't want to have iterations. We would like to get a solution immediately, meaning, can we not evaluate all of the designs in parallel and then get a solution after one iteration? Because that saves us time. And when they say time, they really mean elapsed time. Like we want to do this in 1 day rather than 1 week or 2 weeks. So, of course, the first step is, and that's what we did here, we run it in an iterative fashion. We run an evolutionary strategy that optimizes the car design on the so-called multidisciplinary settings, which means various different simulations are being executed on the car at the same time. And then you see here this very abstract figure that essentially says you have a significant mass reduction while keeping the car safe. And we were able to reduce the development time from 5 weeks to 2 weeks by doing this. with only 180 function evaluations, which essentially boils down to 18 iterations of a population size of 10. But to be honest, 18 is still way too much, because one simulation takes about 24 hours. And then you don't want to wait for 2 weeks roughly to have the result of the optimization. You want to have it faster. And you also see this is a 2006 paper. So meanwhile, the methods have changed significantly. Still, optimization is being used, but it is massively combined with machine learning. And I will get back to the crash problem in a couple of minutes. Going further, you can, of course, immediately see, and I'm a big fan of this, that you can also use this for algorithm configuration in general. So if you replace the word simulator by the word algorithm, then you get a very general setting. You have inputs, you have outputs, you have parameters of the algorithm that you need to tune. And of course, we can do the same as before. We can have an optimizer or a meta algorithm that does the tuning. And then, of course, all of you know we are immediately in the domain of algorithm configuration, hyperparameter optimization. With the typical formulation, we have a set of problem instances. We have algorithm and the algorithm parameters. We compute some function that measures a statistical parameter, for example, a mean across these instances. And then we have the cost values that we get, and we can look for the set of algorithm parameters that is maximizing the performance. And to me, it's completely intuitive, like it will be to many of you, that this meta-algorithm can be an evolutionary algorithm. And Grevenstedt's paper from 1986 was the first example, which used a genetic algorithm to tune a genetic algorithm. So it's a no-brainer from our perspective. I think we all agree on this. So we did this developing a mixed integer evolution strategy. So this is an algorithm indeed that we developed about 15 years ago. It's a very simple idea. You have continuous parameters, discrete parameters, and categorical parameters that you would like to be able to handle in your mixed integer formulation. So you might have continuous parameters that control certain components of the algorithm. You might have discrete settings and categorical settings. And we just, in a very simple way, said, okay, let's use the self-adaptive early trick in evolution strategies for adapting the continuous parameters. Günter Rudolph actually proposed also many years ago how to do it in the very same way for discrete parameters using a geometrical distribution, actually the difference between two geometrically distributed random variables. And Martin Schütz and I proposed also many years ago how to come up with self-adaptable mutation probabilities for categorical parameters. So you are extending the idea of bits to arbitrary alphabet size, like here we called it ND, and then you can actually self-adapt mutation probabilities using the same idea as in evolution strategies. We applied this, so that's the simple message. Obviously, you can use this as an algorithm configurator. We applied this 15 years ago to the intravascular ultrasound image classification problem that doctors have when they put this catheter into your arteries in order to look for how much calcified plaque you have in your arteries and where it is. And here you see a little bit of the difficulties of automatically identifying the plaque. Here, this is an example of a plaque in the artery. And back then, of course, modern machines are better, but back then, this is what the movies looked like, that they had to look at in real time. And I personally don't see anything, as you might probably do. But the bottom line is it's very difficult to reliably identify the plaque, and therefore you would like to have, obviously, image analysis algorithms that support you in doing that. Now these algorithms, and you see these publications are from the time frame 2006 to 2013, these algorithms have many parameters. And here you see that these parameters actually fit the description I just gave you before. They are integer, ordinal, Boolean, continuous, and so on. So you can use this mixed integer evolution strategy that I was just talking about to optimize these 16 parameters, and the results are such that you can easily get a performance improvement in the classification of 40% for the resulting data sets that have been pre-classified, of course. So we have training data in this case. And yeah, it's a very nice and very easy way to use this method for algorithm configuration. Bottom line, evolutionary computation is also a very good alternative for algorithm configuration in general. Let's look a bit further into another application where we did some additional solution mining. So looking at the set of solutions from the perspective of trying to understand the structure of local optima. This is an application which for many years I found already fascinating. We actually started in the 90s with this. It's optical systems. And those of you who have known a little bit about, this, it's actually an extremely interesting world because the problems can be formulated as variable dimensional mixed integer categorical optimization problems, because very often in optical system design, you do not even know how many components to take. So it's already a variable dimensional problem. We published this together with some scientists from ASML in the Netherlands in a optical design conference. And the idea is that we started with a very classical problem in this domain. So here you see the so-called Cooke triplets, and it's a triplet because you only use 3 lenses. That gives you 6 parameters because the lens curvatures are the parameters that characterize a single lens. So you get 2 per lens. And you have to use a simulator to evaluate an arrangement of lenses. And the optimizer is, in this case, only looking into a 6-dimensional space. But you can easily see that you can make this arbitrarily big by adding more lenses, for example. In this area, much of the design is being done by actually using expert knowledge about how to design lens systems, and designing them from scratch without expert knowledge is still a very interesting question. If you look at the objective function, you see that we took a very simple formulation which actually formulated constraints as quadratic penalty terms that have to be minimized, and they get weight factors in front of them. We all know we can do this differently, and of course we want to move towards multi-objective optimization on this problem too, but this is a very good first approximation as we found. And in principle, you want to focus obviously everything on the central focal point. So all of the rays which are being simulated have to focus on one point. And here you see an off-center ray, the red ray here that is characterized here by this red line. Obviously, you are minimizing the displacement from the center, but also subject to a couple of other constraints which are very specific optics constraints. Now, the background is this problem is very well understood. 21 locally optimal lens designs exist and have been analyzed by people. So they are very well aware that there are many local optima, and these 21 are the ones which are classically known. You can look them up in books. They have objective function values in this range. And the idea of this application was, how close can we get with an evolutionary meta-heuristic? Can we find more local optima? And can we do all of this without using any domain knowledge? So we used a niching evolutionary algorithm, and we run this to find multiple optima within one population of search points. Not going to explain all of this algorithm, but the basic idea is that we use a previously developed 1, lambda niching CMAES, in which we are actually splitting the offspring into multiple niches, which are locating or populating local optima. I should say the regions of attraction of local optima, because here we combine this with a local search algorithm from rows 10 to 14. The best solutions which characterize different local optima according to the niching algorithm are still exploited further with the local search algorithm to find the associated local optimum precisely. To make a long story short, on this figure, you see the RMS spot size, which is to be minimized. The local optima that were previously found are all these red stars. So they range in quality between 2 times 10 to the minus 3 up to a little bit around 8 times 10 to the minus 3. All the blue spots are additional local optima that we found. So we actually went from 21 known solutions to 540 known solutions. We were not able to beat the best local optimum that you see down here with roughly 2 point something times 10 to the minus 3. But 540 new local optima are actually extremely interesting for the experts to take a look at. And now we get into an area in which you would like to kind of understand the structure of these local optima. So what we did is, you can do this with 6 dimensions, look at projections of dimensions against each other. And you see that the local optima are located on a high dimensional manifold, and you get similar patterns for other projections of the dimensions. What you can also do is, which is also very interesting, you can analyze the feasible versus the infeasible solutions. So the upper row of solutions that you see here, and these are more than 540, these are all solutions that we evaluated because we were interested in feasibility versus infeasibility. So the upper row is projections of the feasible solution. The lower row is projections in the same dimensions of infeasible solutions. And you can see that they are actually mixed with the feasible solutions. So right next to an feasible solution, you can have an infeasible solution in this design space, which is very interesting. So the next idea, obviously, is to train a classifier, and a very simple starting point was a support vector machine-based classifier that can actually differentiate with 85% accuracy, predicting feasibility. That's still not good enough, so further work is on the way to actually make this better. But of course, it would be very nice if we could predict already from the input vector whether we have an infeasible solution, because then we don't need to run the evaluation, which is not that expensive. But if it's 1 minute, then you can imagine that, and it is about 1 minute in this case, that this is already kind of something where you would like to save that computational effort if you can predict infeasibility. Moving to multi-criteria optimization, we are very interested now in something that people like to call explainable AI. Yeah, that's a big term. I think it's completely sufficient to say we analyze the solutions again, and we're trying to understand the structure of the solutions. But explainable AI is a more fancy term, of course. So one of the applications is buildings for energy, structure, and comfort. Obviously, energy consumption should go down, structural integrity should go up, and comfort should also be optimized. And Michael Emmerich has done amazing work here, where you see a Pareto front. The 2 objectives that you see are to be minimized. So we see lots of dominated solutions. So all of these cloudy areas over here are dominated solutions, which are not on the Pareto front. The Pareto front is the solutions over here, which cannot be improved in one objective without getting worse in the other one. And now you can easily take some subset of this and apply a machine learning algorithm, for example, just a simple decision tree algorithm that generates a decision tree that allows you to characterize some of those clouds, like, for example, the 4 subsets that we have selected here. So you can learn something about the structure of solutions which are on either one end of the Pareto front, the other end of the Pareto front, in the middle, which we call the knee point, or completely dominated and therefore worse than all of the solutions on the Pareto front. So these buildings actually, not all of them, but some of them exist actually, to be honest, and that's a very interesting practical application indeed. And you see that on the extreme ranges for structural performance, we get buildings like that. If we want to optimize for thermal performance, you get high buildings. If you want to optimize for, if they are Of low quality, you get arbitrary mixtures of these two forms. And if you're in the knee point region, then you get some kind of crossover between thermal performance and structural performance. Bottom line, extracting knowledge can then give you results such as long buildings are structurally efficient, which makes sense. And a compromise of structure and energy consumption can be found at the knee point region. We did the same for ships, which is also very interesting. You can imagine that for ships, all kinds of criteria are being evaluated, like, for example, the performance in water, the resistance in water, the ship weight plays a role, but also other criteria like tank size and stuff like that. This is just one of those optimization runs. Again, the green solutions that you see are on the Pareto front. I should say non-dominated solutions. The red ones are infeasible and the blue ones are dominated solutions. So you see a Pareto front emerging between resistance and tonnage. You see on the right-hand side here how these ship forms evolve. Essentially, geometry parameters, metal thicknesses, and positioning parameters are optimized. And at the end of the day, again, a compromise between resistance and tonnage of the ship is emerging. And again, you see that if you want to squeeze out tonnage, then the resistance goes up. If you want to squeeze out resistance, then the tonnage goes up. And at the end of the day, you get compromises like this, where resistance was reduced from the original design to 0.88. and the tonnage from 2,039 tons to 1,748, which is a significant improvement in both objectives. Actually, the maritime engineers are very surprised constantly by the solutions that they get. The new algorithm developed here that was published between 2018, 2017, and now we are constantly working on it, is actually based on Kriging models for the objective function values and radial basis function models for the constraints. So it's also learning the constraints using machine learning techniques. And then we are only using an evolutionary optimizer here for the acquisition criterion, which is evaluated on these meta models. So we are now moving the evolutionary algorithm inside the efficient global optimization algorithm for optimizing the acquisition function and finding multiple solutions on the acquisition function, which is a trick. Rather than the outer loop, it's now the inner loop in an efficient global optimization algorithm. And again, multi-objective optimization, you want to minimize the ship weight, minimize fuel consumption, and maximize uptime. So you get nice pictures like this at the end of the day. And indeed, analyzing this gives surprising insights to the maritime engineers. So you see two objectives characterized here on the X and Y axis, and the third objective indicated by the color of the points on the Pareto front, the light ship weight. And then indeed, you can conclude real surprises for the maritime engineers. So from the initial design, it's possible to increase operational efficiency by 4% and reduce the weight by 13.6%. Or you can go the other way. It's possible to reduce fuel consumption by 10% and reduce the weight by 20%. And again, this is a real-world ship design. So these ships are actually really being designed by C-job maritime engineers. And some of them are even being built because these are real-world applications. Getting back to the car crash, I'm sometimes surprised when I see real-world applications and when I see from an academic perspective what kind of problems really exist in real product development. So let me show you an example that's actually relying very much on an automated machine learning approach for simulation data. It's a complex slide, but many of you do these things every day. So this is just the idea of an automated machine learning approach building response surface models using n different machine learning algorithms. So you see these boxes here, machine learning algorithm 1, machine learning algorithm n. Sounds very complicated. It's algorithms like generalized linear models, support vector machines, decision trees, random forests, you name it, whatever you have. And the simulation data that we use is from a design of experiments. The simulations are being executed. And the nice thing is, in parallel, so you get all of the results after one day. Indeed, you don't have to wait for such a long time. You can then build these machine learning models, optimize the hyperparameters of the machine learning algorithms using cross-validation, of course, to make sure that they generalize well, compare the machine learning models using a statistical test, pick the best machine learning algorithm and model, and then you have a model that gives you the variable importance and the variance even, so the uncertainty of the prediction. And then you can use that further, for example, for multidisciplinary optimization or for solutions places. I don't want to go into the details here. Okay, how can you use this in reality? This is a multidisciplinary vehicle design problem, which has, again, a variety of different applications, a variety of different objectives that you look at, for example, side pole crash, a roof crash, modal analysis, front crash, rear crash, and so on. Now, for each of those, you need a different simulator, but also many of those are actually being discussed and optimized in different departments in an automotive company. So you have different groups internally that take care of different disciplines. That's a very interesting detail, which we will get back to. So these multidisciplinary requirements actually require interaction, communication, and negotiation between these different groups. Okay? So in the paper that was cited in the beginning of this section, we present a procedure for what we call global sensitivity matrix, where the data is being collected from design of experiments. Then you run this automated machine learning procedure. So for each one of the objectives, you get a meta model, a response surface model. Then you can actually analyze the sensitivity of the parameters. And again, this sensitivity analysis allows you to identify impactful parameters. You can also make real-time predictions, obviously, because now you have the meta models and you can actually ask them for what is going to change if I modify one of those parameters in a certain direction. Then you can compute what we call the global sensitivity matrix. And that global sensitivity matrix is actually looking at all of these interactions in a very simple way. You see 20-something parameters in this little table over here, and you see the evaluation of, in this case, Sobol indices to understand the impact of those parameters. And this gives you, in this particular example, for the side pole crash, you might remember the picture that you saw earlier. This is a different car, but again, it's the side pole, coincidentally. You see two parameters which have a very high impact, T4003 and T3353. Now, T4003 is this blue connection, which actually is obviously responsible for stiffness between the sides. So it's kind of taking up some of the force when you have a side impact. And it also makes a lot of sense that this green component at the bottom, T3353, also is very important for the side crash. Okay. However, now we look at different disciplines in parallel. We know the impact of a single parameter on a single discipline, whether it's high or low. And here you can now nicely see that certain parameters are actually having a cross-discipline impact. So this parameter is actually coupling various different disciplines, and therefore clear indication, hey, people from different departments need to talk about this. This sounds like a triviality, but it is actually extremely important to analyze this and to figure out these connections, because it means that this parameter cannot be optimized by one department in isolation, obviously. Likewise, you can say, okay, there are certain parameters that seem to have no impact at all, so we can do a dimensionality reduction for the optimization. You have other disciplines that might only be affected by very few parameters. So in this particular case, only 3 parameters seem to really have the main dominating impact. By the way, if there's no entry, it doesn't mean that the impact is 0, but that it's below a certain threshold, which is pretty small. And then obviously, these 2 disciplines have very similar key parameters, and therefore they might have a similar physics and can actually be considered in a combined way. Very interesting, very insightful, although no direct optimization at this point in time involved. How do we do the optimization here? We do the optimization in a one-shot way, which means these machine learning models are now being used by optimizers to predict the location of an optimum and the confidence about the prediction. And then you evaluate the resulting solutions with the simulator again. And then we can go even further. So this is just one example. Sometimes industry is not interested in finding the optimal solution, but finding a feasible design space in which any design would be an acceptable solution. That's what you see on the left-hand side. We call that solution spaces because it's actually often very important for automotive companies to have a solution space rather than an optimal solution. And then, of course, multidisciplinary, multi-objective optimization is also very important for them. I need to speed up a little bit. I wanted to give you a few production process examples too, where we actually start with machine learning and then optimization kicks in at the end. And one of the examples is steel and automotive, and I will also talk briefly about a chemical process in the remaining 6 minutes, so I think I will be able to make that. A long time ago already, we started with a research project in cooperation with BMW, Leiden University, Tata Steel, that actually looks into the role of steel in the automotive industry. On the one hand side, steel production and steel quality optimization. On the other hand, the forming process in the automotive industry. One of the big issues that the automotive industry has is that they would like to understand whether a coil, a steel coil that they get delivered, could potentially be causing issues in production. It's within specifications, so they accept it because it fulfills the required specification. But it might still be an outlier in production. So what you need is some kind of anomaly detection that looks at the data about the coil and then automatically flags it as an anomaly. This one you can see immediately what they actually did here, which is what the steel suppliers sometimes do. They welded together 2 different production coils, and the welding point you can see here indicated by the arrow. So you get information about oil, about magnetic conductivity, which is called IMPOC values, about thickness, about roughness of the material. And here you can clearly see, even by visual inspection, that this is obviously an outlier. I say by visual inspection, but you don't want to do this because for 20,000 coils a year that an average automotive company would get from their suppliers, you better have an automated process to do these kind of things. We then developed a very high-dimensional global outlier score anomaly detection mechanism that actually is looking into an 800 and more dimensional continuous parameter space, looks at a global outlier score, defines, computes a global outlier score. And you see this here for this coil. The red area, the red marked area is the new global outlier score that we developed, was published in a paper at an IEEE conference. The basic idea is that the whole area, rather than only the disruption that you see here indicated by the blue curve, the whole area which is an outlier is being characterized and marked by the gloss outlier score. Again, here you would say you can see the transition in the oil levels. Here it's already much more subtle. And again, this coil is indeed very different from normal coils and therefore is characterized as an outlier. That project was finished in 2019, 2020, roughly. And then we went on, though, as another part of this project, to go into supervised learning, where we predict a quality measure. It's, I should say this, very, very difficult to automatically measure quality of formed parts in the automotive industry. So we did this manually because the experts can, of course, classify the quality, but it's really by manual inspection. The first thing to start with was, again, a simple decision tree. We learned the decision tree on the classified data. You get some kind of nice result with the decision tree. And indeed, if you look at the first node, you see an epoch value criterion, which actually determines the split at the highest level. And in fact, if you plot all of the parts, so the part numbers on the x-axis and the epoch value on the y-axis, you see that this is indeed a feasible split that indeed allows you to differentiate between good parts and bad parts, although, of course, many, many good parts are also under this epoch value, and the number of bad parts, obviously, is extremely small. So you need additional techniques here, such as class imbalance handling. You need, obviously, also ideally a better quality measure than just saying okay or not okay, because there could be many reasons for not okay, which definitely don't fall into the same class. But it's a starting point. Then we went to a second measure that actually is a continuous measure, but not really of quality, more of precision. And in order to predict that into the future, you need to know exactly what the material is that is coming next, because you get the steel plates on the stack, and the stack, of course, has a certain order. So it's all being cut from the coil. And therefore, you need to know exactly which part is coming next, what is the sequence of parts that I can expect, what are the material parameters, and then you assume fixed press cylinder forces. So you are not changing anything in the press production. And then you can predict, as you can see here, over a certain prediction horizon, qualitatively, the variation in this quality measure, I should say in this precision measure. All of this, of course, the whole idea is to put this into a process framework in which you go all the way from the initial stack of cutted parts through the press to the formed parts, and ideally continuously optimize the press shop parameters. Now, since quality is so difficult to measure, we also looked into unsupervised learning for recommending process parameters. This paper won an Industrial Impact Paper Award at the conference where we published it, because it really is being used in practice. So in the current situation, it's very difficult to find good process parameters, and people are extremely reluctant to experiment on the press, as you can imagine. So they put a lot of expert knowledge into the process, and they say, this is fine, we are happy with it. And if you look at this diagram, it simply gives you the frequency of the different configurations that were used on the press. So you see that the most frequent configuration was used in about 13% of all cases, and that only about 30-something configurations are used at all, I should say, out of roughly 6 to the power of 6 or 6 to the power of 8 configurations, order of magnitude. Also, there's a lack of inline quality data, so it's really difficult to learn the relation between blank properties, process parameters, and quality. So what we did is, this is a complex slide, but we actually used the data where we have material parameters, and we know that the quality is good, in order to build a classifier that selects the appropriate configuration out of those 30 configurations for a given new part. So you are only using data about good parts to train the classifier, and then you say, hey, now I know the material parameters of the next part, therefore configuration 20 should be the right configuration according to what I've learned before for this particular blank. Now you should also know that you are not changing the press parameters from one blank to the next, because that's impossible given the frequency of the production. You have like 26 parts per minute, order of magnitude. So therefore, these transitions need to be done continuously and slowly based on a forecast that you have about the blanks. But then if you do this without knowing the part quality, you get an extremely high accuracy in the settings, which is, we should say, weighted F1 score, because that's more important here, of 92%, which is extremely close to the situation in which you know the part quality. And this is being used in applications, and indeed you can show that it is optimizing the precision of the forming as opposed to purely running it through the human operator. The performance is comparable and sometimes better, as you can see here from this curve, where the deviation between the target and the real value is actually higher when the operator is operating it than if they call it the AI, of course it's just a classifier, than if the AI is operating it. I want to come to the end, but only with one more example, which is actually being done in my company, which is called IVUS. So this person is the COO of a chemical company in a small town in Germany. And they had a big problem. They had a out-of-spec product, which in 50% of all cases wasn't of the necessary quality, and therefore they had to get rid of the batches after production, which of course is a big problem. And they were even thinking about dropping the product altogether. They gave us data about 58 production batches, 19 sensor signals, about 3,500 records per batch. And then indeed, and this is the bottom line message, solving such a problem is very hard to do automatically with automated machine learning or similar techniques. You always need to talk to the experts. You always need to understand their needs, their data. The data is horrible, as you can imagine. It is always horrible and always worse than you can imagine it to be. So you need to do significant data pre-processing, which also cannot be done automatically. You need to do an exploratory data analysis to understand actually what does the data look like. And it is really boiling down to visualizations, to box plots and so on. Then you need to do some substantial feature engineering because it's all time series. Then you can apply machine learning finally, and then you can actually speculate and interpret and deploy what you found, but only together with the client, because they will tell you, oh, we forgot to tell you this and this and this. And then at the end of the day, you can actually try something on the real plant, which really made me nervous, I must admit, because after all, you really need to trust what you found in the data. And then at the end of the day, all batches can be sold, 100% perfect product. And the problem was found and fixed. And of course, this is the kind of applications we are aiming for. This is really what we want to see in reality. And still in real world production processes, these success stories are rare. And in conclusion, that is also part of what I want to say. So my personal conclusions are that while new algorithm development is continuously ongoing, we go from data models to model-based optimization. Every application is different. It requires expertise. It requires domain expert cooperation. But it's still very exciting for me to go all the way from applications, from algorithms to deployment. And AI in engineering and in production is still relatively new. And every single person I talk to is completely ROI focused, and that is a good thing because it's challenging us, because they indeed say, how much money can I save? Can you guarantee this? And